We are now ready to move to chapter 2, where we are going to study how we can rotate basis state, and that will lead us to the matrix mechanics. On this first part of chapter 2 that I'm going to cover in this screencast, we are mostly going to focus on rotation, and we are going to introduce the notion of operators. And in particular, we are going to introduce two types of operators, two examples of operators. The first one will be the rotation operator, and then after that we will introduce the generator of rotation. The generator of rotations is actually a very important operator for which we will calculate the eigenvalue and eigenvectors, and they are very specific and special compared to our Stern-Gerlach experiment. So far we have worked in the quantum state, and we have decided to create these states where those quantum state vectors live. So this is essentially creating a new world where we have put those vectors, so those kets, which have this particularity that they do include all the information you can get on your system. That's one part. And on the second part, they do have all the properties that you need so that we can understand the Stern-Gerlach experiment. And actually experiments, more than one, so there are 5 of them. And so now that we know how to calculate probability amplitude and probabilities, we are going to see how we can modify the state vectors. Okay, first, representations of ket and bra. We've already done this. We represent ket and bras on basis, a complete basis. And I'm going to here move from this formal representation to a more usual representation using vectors and column vectors and row vectors, things like that. So we know that for the spin 1/2 particle, that actually is the one we've been focusing on for the Stern-Gerlach experiment, any state vector can be written as a superposition of the basis vector plus z and minus z that corresponds to the deflection upward and downward in the Stern-Gerlach experiment. And what really makes a state vector unique, or distinguishable from other state vectors, is the choice of C plus and C minus, which are probability amplitudes, and they are obtained by the equation there. Now the thing is, we can know how much there is of a states aligned in one vector or the other, and we get the probability by the square modulus of this. Another way to do it is to say that we are actually, the bracket is really a dot product, which corresponds even classically to a projection of one state onto another. So in other words, we could consider C plus and C minus as being the components of the states on the basis plus z minus z plus z. Okay? So if we go back to this equation that I had on the previous slide, we can write the state vectors just as a column vector, just the usual way that you've seen it. So it's just kind of coordinates, if you want, just like coordinates. Of course, we know that these coordinates depend on which basis we use. So it's not a bad idea, as you get used to this concept, to explicitly state what basis you use. For example, in this notation, on this box on the right-hand side, we show clearly that it's a SZ basis. And when we do that, we can write a general state, so long as we know which basis we are using. And of course, we can have something specific about the state themselves that can be the basis vectors themselves can be represented in this way. And clearly, if you remember the notions that we've obtained from the Stern-Gerlach experiment number 2, the dot product plus z should be 1, and the dot product minus z plus z should be 0. So it's the probability of finding a plus z state incoming on a Stern-Gerlach experiment z to be deflected downwards. Of course, this is 0. This is what we get. And likewise, we can do for minus z. In this case, we get 0, 1. Nothing really surprising other than the fact that we are formalizing everything that we are trying to do here. Now, of course, we can do that for other states. And if you remember how we build the states plus x after the analysis of Stern-Gerlach experiment number 3, we found that we had 1 over square root 2 coefficient for both the plus z and minus z basis. And in other words, we can write that state as a column vector, just like written on the right-hand side there. Obviously, we can do the same for the plus y state, the one we obtain after Stern-Gerlach number 4 experiment. And we can, Stern-Gerlach experiment number 5. And then we can move on like this. In any case, we find a fairly convenient way to represent the different states using this basis, and now using vectors, and we will see that will allow us to use matrix algebra to make things a little bit easier to calculate for us. Now, we just spoke about the ket representation. Now we can talk about the bra representation, which is obtained as a dual as the ket. And we know that we can write a bra in the following way. Just now the C plus star and C minus star are the same as the C plus and C minus from the ket representation, but they are the complex conjugate. And this comes from the fact that we are trying to write the state vector, the bra state vector, on a basis of plus z and minus z bra basis vector, plus z and minus z. So we can, now the reason why we introduce those the bras is to calculate brackets. And what we really wanted to do is to be able to use a bra and a ket, put them together, just like on the last line here on the slide, and being able to get a scalar. Now, it doesn't take rocket science to know that if we can represent a ket as a column vector, the best way to represent the bra vector would be to have a row representation. That way, if we do a simple matrix representation like this, a matrix multiplication between a row and a column vector, we obtain a scalar. So we're going to represent the bra vector that way, and that will allow us to do all the calculation, all the dot products, and the probability amplitudes that we need. So remember, something that is really important to remember, each time you write a row like this or a column like this, we have to remember that it is written in a specific basis. Do not be tempted to use different bases for a bra and a ket that you are going to multiply. That's going to give you answers that are really wrong. And you are going to create a new kind of physics which turns out to be obviously bogus. Okay. Now, another example that I would like to show you is how do we get minus x in the representation as z. We've never spoken about minus x much, I believe, so far, but we have spoken about plus x. So we know that plus x looks like this. So plus x represents just this column vector that was 2 slides ago. Now we know a property of plus x versus minus x is that the dot product between minus x and plus x should be 0. Remember, what is the probability of finding a state that's initially in plus x into a minus x state after a Stern-Gerlach x state? That's what it really means. So in other words, we know this. It has to be 0. So thus, the best way to get that is to find that minus x state should be given by that column vector with 1 minus 1 on the 2 element and a normalization factor in front. So I like to note that here that we have a phase factor delta, EI delta, because calculating the dot product does not give me any information about that particular property. So we see that if we use that choice, indeed, the dot product minus x plus x is equal to 0. We can, of course, the choice of that prefactor, of course, give me normalization that the minus x state, the probability of finding a minus x state after a measurement of the Stern-Gerlach x state for an input and on minus x is equal to 1. That's what really this means. Okay. So we can choose delta equals 0 for the overall phase again, because we can choose the overall phase of the state minus x, no problem. And then we find that plus x and minus x are obtained easily as 1, 1, with 1 over square root 2, and 1 minus 1. And we can do the same with plus y minus y. You will remember that plus y was 1 over square root 2 plus z plus I over square root 2 minus z. So you can calculate the minus y state in that case. And then you obtain, of course, this result that I really think that everybody should spend a couple of minutes trying to get. I like to attract your attention going from the left to the right. really from a matrix standpoint, because a vector is a matrix, it's just not a square matrix, the plus y, the bra plus y is just the transpose conjugate of the ket plus y. So there's a reason why not only you go from column to row, but you also change I into minus I, or minus I to I, as in the case of the minus y bra and the minus y kets. Okay, so now that we have all that kind of this very simple tool, we can calculate the probability of a spin 1/2 particle, for example, which correspond to Sx equal h bar over 2, to be found to have Sy equal h bar over 2. So I invite you to try to make a sketch of the kind of experiment you would need to do to represent that question. Of course, from a mathematical standpoint, all we need to know is to calculate the bracket plus y plus x. So we need to have plus x and we need to have plus y. So this bracket plus y plus x is exactly what I need. Is the probability of finding a spin 1/2 particle that comes out of the top channel of the Stern-Gerlach X to be found in the top channel of a Stern-Gerlach Y. It's exactly what this is. This is a probability amplitude. Now, what's nice is because we know how to write plus x and plus y in the plus z representation using rows and column, we can calculate things very simply. And we end up with a very simple way to calculate things just by using numbers at a level that's only using some fairly fundamental complex number analysis. And we find here, of course, that the probability in this particular case is 1/2, as expected from Stern-Gerlach number 5. Okay. If you go into the book, there is an example that's worked out. This is an example for a given state vector, a given state vector. It's given by this expression, and again you can calculate the amplitude, the probability amplitude, to be in Sy yielding h bar over 2. In other words, you calculate the bracket plus y psi, and you will get that property. Okay, now let's try to move to the end of this section by talking about now representation that we have. We have the representation that I worked so far was the SZ representation, but in fact we can use any representation as long as it works. So if most of my Stern-Gerlach experiment are SGX, it might be a good idea to use the SX representation. But if most of my Stern-Gerlach experiment I'm interested in are SGZ, well, the plus Z minus Z representation is probably the best. So we could write, for example, a state vector on the plus x minus x basis, just like this. And then, of course, write a column vector, which, of course, are different depending on the basis you use. Nothing really surprising, other than the fact that you should remember that. So the question is, which one is of these two representations here is the most accurate? Well, of course, accuracy has nothing to do with anything here. They are obviously equally accurate. They just represent it in a different basis. Now we can move to another topic. It's the representation of rotations and how we can use rotations to change a state vector into another one. So the question that we can have is, suppose that you have a state that's along Z, that's actually correspond to a magnetic moment along Z, and we would like to transform it into a state that has its magnetic moment line along X. If you were using purely classical geometry, I would say, well, all you need to do would be to rotate the state plus Z around the y-axis by pi over 2. And that's exactly what you would need to do. So let's suppose that we are not working with classical physics at all, but that we can find such an operator that would actually rotate one state into another one. Okay? And we would call that operator R hat pi over 2j, just like it's written on the right-hand side. So the reason why we put a hat is because it's an operator. In other words, it's not just a number that we don't just multiply plus z by a number. We actually transform plus z with rotation operator. So one way to look at it is that if you represent plus z as a column vector as we did in the previous section, R would be a 2 by 2 matrix, for instance. We still don't know what are the elements of that matrix, because remember, this is not your simple algebra that we looked at so far. This is not just classical physics, this is quantum mechanics, but we are going to work it out. So this is independent of the representation. Again, that expression there is an abstract representation that has an abstract notation that has nothing to do with the representation. I just mentioned to you that the hat is useful for knowing that this is an operator, not just a number. And this operator, of course, rotates a state vector, not a number. There is no such thing as rotating a number anyways. So we can apply this rotation operator now to any state vector, any state vector psi, and we can do that because we know the action of the rotation operator on each basis, plus z and minus z. So the rotation of plus z will give me plus x, rotation of minus z will give me minus x, and I end up with the rotation of the general state psi as given by the last sentence, the last line there in the red box. So what about the operator acting on a bra? So we know how an operator acts on a ket, and what I'd like to know is that what is the bra that corresponds to the rotated ket? Okay, so if I had to find the bra that corresponds to the rotated ket, how would I do that? That's the question, and this is by imposing a number of rules that we expect to have for rotation. We'll be able to calculate this. So in other words, this is the same as saying what I just asked. What is the bra plus x? Well, let's suppose we don't know so far. So we are going to call it the adjoint operator. Just going to introduce it there as a definition, and that adjoint operator will act on the bra plus z, and it will provide the bra plus x. I would like to make sure that it's clear here that the operator, the adjoint operator, so the dagger part, does act on the right-hand side of the plus z. By the way, I could have called it alpha p r s, whatever you wanted. I just decided to call it r dagger. We have no idea what it is so far. We just know that it's an adjoint operator of r. Okay, now the only thing that we really know about plus x compared to its bra and ket is that the probability amplitude plus x should be 1, just like the probability amplitude plus z should be 1. So if we substitute the value of plus x, the bra plus x and the ket plus x in that expression, we obtain the following formula, equation, that simply shows one thing that's obvious, is that r dagger r should be the identity operator. So that red box should be the identity operator. So in other words, the operator that operates on a bra vector so that it corresponds to the operator that operates on the ket vector should be the inverse of it. Right? That's what it means. R dagger r should be equal to 1. So what does that mean really? It means that r should be unitary. So we have a unitary operator, which is quite interesting because that means that we can go back to all the linear algebra, the property of linear algebra for those operators, which essentially impose that we have a conservation of probability if we rotate the whole thing, which is not really a big surprise. Now here is where we are going to make a big step forward and finally be able to connect what we've done to the measurements that were made with the plus z minus z state. And this is going to be by the introduction of this concept of generators of rotations. We are going to do that right now. So what we will do is to define the rotation operator of an infinitesimally small angle d phi, for example, around the z-axis. So this is the reason why we have a vector k there. And we are going to write it that way, that's written right there. Okay? So that result is, let's try to make sense of this. First, if d phi was equal to 0, the rotation would be the identity operator as expected. That's good. And second, there is no d phi square, of course, or d phi cube terms or higher order terms, because since d phi is infinitesimally small, all those terms are negligible, in fact, vanish. So we understand already the shape of this equation. That's good. And we are going to call Jz, which is an operator, we are going to call it a generator of rotations. So you can say, well, you know, it's just one way to write things. We don't learn much anything. Yeah, it's true. We do not learn much anything with this yet until we find some very fascinating properties of Jz. So one thing that most students get a bit confused about is why do we put I over h bar there? Well, the reason why we put I over h bar, or even actually minus I over h bar in front, is just for convenience. First of all, we put h bar to ensure the Jz will have the units of h bar. Again, that will come obvious in just a few minutes. Second, we put I there because if we didn't put I, Jz would not have the properties that we want. And second, it doesn't really matter what we put in front because since I've not defined Jz just yet, I over h bar could be very well be included into Jz. That would work just fine. Okay, so don't get really too scared about that expression. It's actually not that complicated at all. So just like I said, we have an operator Jz, and we would like to find the operator, the property of Jz. So before we go there, we can think about the adjoint rotation. So remember, we introduced the notion of adjoint rotation so that we can find the corresponding bra to a ket that was rotated by a rotation r, and we find that that rotation that we have to apply to the bra is actually the r dagger. And on top of that, to preserve probabilities, we find that r dagger r should be equal to 1. In other words, the adjoint r dagger should be the inverse rotation. Okay, that's what we've done so far. So we can write the rotation, and maybe we should just stop at, I'm sorry. Okay, we should write the r dagger simply using the definition of r, and of course the I becomes minus I, and the Jz becomes Jz dagger. All the other parts are real numbers, so we don't have to worry about them. Okay, but at the same time, as I just mentioned a second ago, r dagger is the inverse of the rotation operator. In other words, r dagger of an angle d phi is the same as a rotation r of an angle minus d phi, because of course rotation minus d phi is the inverse of rotation of d phi. So we are doing pretty well. And so if we want to impose this, and if we replace d phi by minus d phi on the top left equation, we find that the only way for this to be true is for Jz dagger to be equal to Jz. Okay? So if we use this generator of a rotation, of the rotations, and using this expression that we have introduced in the previous slide, we find that the fact that r is unitary imposes the generator to be Hermitian. And of course, at this time, you see why we didn't put the I instead. We put an I in front of Jz, because if we had not done that, we would have not had that Hermitian property. We would have had to define another operator and have an extra step. Okay. There is another way to prove the exact same thing, is by explicitly doing the r dagger multiplication like this, and this is what's shown on this slide. And by imposing that r dagger r is equal to the identity operator, you can find that the left-hand side would only be indeed the identity operator if Jz dagger is equal to Jz. And the reason for that is because we can drop all the high-order terms, the d phi square term, which is obviously negligible since we have an infinitesimal small angle. Okay, now we are ready to move one more step, and in fact this is a very important step, and even though it's not crazy, it's certainly the hardest mathematical step that we are going to do now. Okay, so we have worked on the infinitesimally small angle rotation. So that angle d phi can be written as a limit of phi over n for n going to infinity. Okay, that's one thing. If I want to have a rotation of angle phi, now what I need to do is to apply that rotation of angle d phi n times, right? Because I'm going to rotate by d phi, and then d phi, d phi, d phi n times until I get to phi. So in other words, I have to operate the infinitesimally small angle rotation to a power n, and I obviously have to take a limit over n to goes to infinity, since the angle is supposed to be infinitesimally small. Okay? So in any case, we end up with that expression, and I like to attract your attention that n shows up at two places, right? And for those of you who maybe remember having seen this in other courses or in other contexts, you can see that this expression is actually the expression of the exponential, the complex exponential minus ijz phi over h bar for the argument. This is really an important result. So I'd like to make two comments. The first comment is that since r is unitary, its effect on a vector should be on the effect on, for example, the z vector should be, the plus z vector should be simply to change the phase, and this is what we see there. We have kind of a phase factor, kind of. You know, it's not quite a phase factor exactly, because this is more complicated. We have an operator. In fact, this is the second point I'd like to make. This exponential of an operator is really an abstract object. It's really difficult to see how that would work, how we can apply the exponential of an operator. So usually what we will do, we will re-express this on a Taylor series. But for compactness, it's actually a very nice thing to do right there. And we are going to do that. And I'd like to prove that. Okay. That last equality, I think it's important to prove it. And the way we'll prove it on the next slide is to show that the Taylor series on the second part of the second part of the equation, the third part of the equation are the same. So if we can prove that the both Taylor series are the same, therefore we can certainly make sure that the both expressions are the same. So we are going to prove it, and of course Taylor series are given by this expression, and the Taylor series of the exponential for the right hand side is the easy part, of course. We find simply that we have the expression that's written on the slide, and we have simply now have to calculate the Taylor series of this expression that you might be a little bit less used to calculating. I'm not going to go into detail, but I will provide you the detail in the next slide. But I invite you to pause this screencast and work out the math and make sure you understand what this is. So on this slide here, it's a little bit busy, but this is informational slide. Explain how you calculate the different derivatives, and then you end up with the right answer. Okay, so I invite you to do that. So far the summary is that we have a rotation operator. We know it's unitary. And then we know that we can introduce an operator Jz, which is called the generator of rotation. And when we do that, we find that Jz is Hermitian. So the natural question now that we have is, what are the eigenvectors and eigenvalues of Jz? Why do we have that question? Because if we are a Hermitian operator, it has real eigenvalues. In fact, and we will see this in this course many times over, in order for an observable anything that can be observed, so observables in nature correspond to a Hermitian operator. In fact, this is because they correspond to real eigenvalues, which is exactly what you would measure. So we're going to get that in more detail, but Jz, I can tell you already that Jz corresponds to something we can observe, and in fact we have already discussed it. So you probably have an idea what it could be at this point, since we only discussed one experiment. Okay, so the eigenstate eigenvalues, in order to get there, we should just reflect a little bit on what would happen if I try to rotate the state plus z around the z-axis of any angle phi. Well, what we expect is that we would still have the plus z vector, but probably times a certain phase factor, but certainly not changing the length of, the normalization property of plus z, or the rotated plus z. So now we can actually go back and use the expression for the complex exponential and write the Taylor series. As I told you, it's not possible to calculate directly the exponential of an operator unless we are in some circumstances where we know the eigenvectors, but we are not there yet. And so we write this, right? It's the typical expression for the exponential for the Taylor series for the exponential. So we end up with this, and I reproduce it on the next slide. So look, what we are looking for is for something that when we rotate plus z around the k-axis should give me something that is proportional to plus z times the phase factor. And then you see from this equation that the only way this could be true, so when I say this, I mean that the right-hand side will be proportional to plus z times the phase factor. The only way to have that for any angle phi, and I insist for any angle phi, is that that plus z, the ket plus z, is an eigenvector of Jz. Okay? And you can, the best way to prove this to yourself is that suppose it were not the case, okay? Suppose it were not the case, then the expression on the right would have a component along minus z, let's say, and then you would never be able to cancel it from the other terms, and thus you would end up with the expectation that the rotation of the plus z vector around the z-axis would no longer be aligned with the plus z-axis, which is not appropriate conclusion. So we show by thinking about this, that plus z vector is indeed an eigenvector of Jz. Okay. Now we also know that the constant, so the eigenvalue, is real since Jz is an Hermitian operator. So Hermitian operator have real eigenvalues, and the obvious question we have now is that what is the value of the constant? Okay. And so what we are going to show is that the eigenvalues corresponding to the eigenvector plus z is in fact h bar over 2. This is the magnetic. This is related to the magnetic moment that we obtain. So the orbital, the spin angular momentum that we obtain from the Stern-Gerlach experiment. By the way, I didn't discuss about it yet, but we can have the same discussion for the minus z state vector, the basis vector, and we have the same thing with the conclusion minus h bar over 2. So the way to show this is to apply Jz to z and get an h bar over 2 and times everything we need. So let's go back to the previous slide. So right on this equation, we know that Jz applied to the z ket is actually h bar over 2 times the z ket, and so on and so forth. So we do that, and we end up with this. And again, if you remember your Taylor series of the exponential, which we have already seen 3 times in this screencast, we end up with a state vector plus z that is rotated into a plus z times the phase factor, which is exactly what I wanted. Now, this is simply a proof that that solution works, okay? If that solution works, then it must be the right one, because it is only we can argue, and we'll have a discussion more in detail about this. So this is more an intuitive discussion. We know that R has only 2 eigenvectors, since we have a 2-state problem. So we only have two eigenvectors and eigenvalues and eigenvectors in this case. So we found the 2 eigenvalues that are plus h bar over 2 minus h bar over 2 for the 2 systems here. Okay. So the effect of the rotation is to have the kets pick up an overall phase. Okay. I like to also attract your attention, and we'll talk about that again in a future slide, probably in the next screencast. When let's suppose I rotate by 2 pi, we would expect classically that plus z would transform in plus z, but you see here it's not the case. In fact, plus z will transform into minus plus z. So it is the phase factor that it turns out it's actually even though we cannot measure the phase factor, there are experiments that allow to demonstrate the existence of this minus sign. Okay. The next thing we can ask is, what's the effect on another state? For example, let's think about plus x. So a rotation of pi over 2 would yield a state equal to plus y, right? If we rotation around the z-axis, of course. So that's what I write there. So the rotation of an angle phi around the z-axis, which is k, of the ket plus x will give me, can be applied to each state vector, basis vector, sorry, plus z and minus z, and we end up with that formula we have right there. This is something that's pretty fundamental, elementary. Now, if the angle is pi over 2, we find that the expression becomes simply that indeed we refine the plus y ket vector that we have already encountered in the previous screencast, times the phase factor E minus I pi over 4, which does not matter in terms of probability amplitudes. Okay, so all this formalism seems to work pretty well in terms of rotating one state into another. And we are starting to really move along very well with our quantum mechanics, because look, we had a property which is the spin of the electrons. We find that that property can be measured by looking at the eigenvector of an operator, which turns out to be the operator corresponding to the generator, of the rotation operator. So one thing that is true, if we remember that the rotation operator can be written as an complex exponential, it turns out that when we rotate by 2 pi along the z-axis, or for example the plus z state, instead of finding the plus z state at the end, we actually find a phase factor corresponding to pi. In other words, the complex exponential corresponds to a minus sign. So it's quite interesting that when you rotate in this quantum space, the plus z vector around the z-axis for 2 pi, you do not get back the vector, but you get minus the vector. And it's actually true for minus z as well. Of course, we know that the overall phase does not matter in terms of changing the probabilities. So the probabilities that you would measure using that state would essentially be the same. But there is really an intrinsic phase that you pick up when you rotate by 2 pi. And we will explore this further as we move along in this course. Now, let's try to move on and try to work on a different type of operator that we have encountered so far in the Stern-Gerlach experiment, and that's going to be the projection operators, which when put together are the identity operator. So one thing that you should remember by now is that the fact that you have a plus z minus z complete set means that any ket vector psi can be written as the way it's written in this red box here. What it means, though, is that each coefficient is given by this probability amplitude of finding the state psi in the plus z channel when you do a Stern-Gerlach experiment, and so on and so forth. So we've done that. But one thing that we can also do is to find that it turns out that if we use the operator in the blue box there, which is obtained just by building with the bra and the kets plus z and minus z, if we apply that operator to psi, we would exactly get the red box. In other words, that operator is the identity operator. And it reminds us about the modified Stern-Gerlach apparatus that says that starting from a given input, a given psi, the modified Stern-Gerlach apparatus, where the magnetic moment is aligned along z, correspond in separating the plus z, separating the incoming electron into a plus z channel and a minus z channel, and then putting back together. So what we said at that time when we look at this experiment was that adding these two channels back together was equivalent to using an identity operator. We saw that it doesn't make any difference in the probabilities that we will measure when we attach the other Stern-Gerlach experiment after this modified Stern-Gerlach experiment. In other words, this modified Stern-Gerlach experiment is really an identity operator, but now we understand a little better what those two beams, actually those two separated channels, correspond to. They correspond to both sides of the equation. I mean, both sides of the equation in the blue box between on each side of the plus sign. So that's really what it is. It's actually a pretty deep statement. So we have this minus z there and this plus z on the top. Now we can go further, because suppose now that we decide to block one of the two channels in the modified Stern-Gerlach experiment. What we've really done is to actually select those states that project out on plus z. And we could do, of course, the same on the bottom channel for the minus z. In other words, we can see that we can separate the identity operator into we can re-express the identity operator as a sum of two operators, one being a projector on plus z state and the other one on minus z state. So we call them this plus z and the pz and the p plus and the p minus projector operator. Okay, so we of course call them projectors because when we apply p plus in the state psi, we get a vector that is actually proportional to plus z. So we are projecting the state on the plus z, and likewise for minus z. The fact that we have a complete relationship, so completeness of the basis plus z minus z, simply means that if we add the projection on one vector plus the projection on the other vector, of course, we get the identity. That's what it really means. So we have a complete representation of the problems if we use this basis, this complete basis. That's another way to say it. Now we can think about, we have this operator P plus and P minus, and we can think about the eigenkets. And here, all we have to do is to remember what an eigenket of an operator is. An eigenket is that ket that when you apply an operator to it, you get another ket that is proportional to the initial ket. So clearly, we see that the two eigenkets for P plus would be the plus z and minus z ket, obviously, because when you apply P plus and plus z, you also get plus z. And when you apply P plus on minus z, you get 0, which simply means that the projection of minus z on the plus z direction is 0. Nothing really surprising here, other than the fact that we found the eigenkets of P plus. And then what we find, of course, is that the eigenvalues will be 1 and 0. So this is an interesting thing to do, because we can also apply it to P minus. Now we understand a little bit better also when you apply the Stern-Gerlach experiment, the modified Stern-Gerlach experiment, multiple times. All we have to do is to use the chain rules for the bra and the ket. And because what's interesting when we apply two projection operator is that what comes out of this, and this is the first sign of the equation there, is that we end up with brackets plus z, or plus z, or minus z minus z, which for which we all know. So it's like reduction. It's like we can reduce the expression and make it very simple. And seeing that applying P plus or the P minus projection multiple times is equivalent to applying it once, which again is not surprising. Once you have projected a state along a certain direction, if you keep projecting the state of the same direction, obviously, you do get the same answer. That's not really a surprise, but using this Dirac notation, we find that pretty nicely. Of course, if we apply two different operators sequentially, we find that we get 0. And then again, we can use the properties of the brackets of between plus z and minus z to demonstrate this. Again, what it means is that if I project my state along the minus z direction, and then I try to project the result of that projection on the plus z direction, I get 0, which sounds to be pretty obvious. But you can check that using the Dirac notations and using the explicit calculation of those product of operators. Okay. Of course, we can move beyond the plus z minus z. We can, as long as we have a complete basis set, we can always write this expression. I like to, of course, attract your attention that here we are working on a two-state problem. We always have either plus z or minus z, plus x minus x. But this can be generalized to any complete basis, regardless of the size of the basis, so long as it's complete. Okay, now if we go back to the experiment number 4, and remember the experiment number 4, the idea was that we had an output of Stern-Gerlach along z, and we basically were selecting, in the first box, we were selecting the states projected on plus z. The second box was this modified Stern-Gerlach x, which now we know was essentially doing nothing. It's an identity operator. And while the other one, the last one, the Stern-Gerlach along z, again select the plus z state in this particular setup. Okay. So what it means mathematically, using everything we know, is that we started on plus z, that can be written on the basis plus x minus x, the way it's written right there. Right? Nothing really new for you. We use the identity operator plus x minus x, right there in red. And then it follows that if I look at the projection of that state on the minus z state, okay, we know it should be 0, right? But if we use the representation plus x minus x, we get two terms, okay? But both of these terms are not 0. In fact, they are both clearly non-zero. each individual state. But okay. So all I need to do, so we have the sum of two amplitudes and neither are zero. Of course, the sum is zero of the two states. That means that this projection of this plus z state on minus z should be zero, but the fact that I express the state on a plus x minus x basis, which again is purely arbitrary, shows that the output comes as zero because we have a cancellation between two amplitudes. So let's try to say what it means, okay? It's very useful to express your mathematics in plain English sometimes. That makes you understand it better. All right, so in blue there, we find it is the first box is that if we have a state in plus z, time, we look at the probability of finding it in minus x. And the first part of this blue box was if we have a state in minus x, what is the probability of finding in minus z? Okay. Okay, good. We can do the same for the other box. I'm not going to spell it out, but this is what is written there. And of course, we have to multiply those amplitudes. So we have to multiply all those things together, and let's see what we get. Well, the full probability will be the square of the modulus, and we have, of course, the square of the modulus of a four terms, so we end up with all those terms here. We have the probability of finding a state measured in Sx equal h bar over 2 times the probability of measurement of Sz to be minus h bar over 2 when the final state is correspond to plus x. This is the blue box. And we have the similar thing for the second term. And finally, for the other two terms, we have some cross product. And I invite you to calculate that each term is in fact plus 1/2, so the two first terms on the first line at plus 1/2, and the sum of the two other terms in below is minus 1/2. We actually did that in class. It's very straightforward to do as long as you can multiply 1 over square root 2 by 1 over square root 2 and have the minus sign at the right place. So I think it's very important to do it one more time to make sure that you understand this. Okay, now that we have worked on a number of operators, we are going to work on their representation. In fact, we are going to see that the operators will be represented by matrices, just the same way as kets are represented by column vectors, and bras are represented by row vectors. So if you remember what we did before for the bras, for the ket, sorry, up there, psi and phi, we could express them on a basis of a complete basis, which in this case was the plus z minus z basis. So now what we are interested in is to say that actually the ket phi is obtained by the application of the operator A on the ket psi. So that's what's written on the right hand side of the blue arrow right there, where I substitute phi and psi by the expression on the left hand side. Now, as usual in linear algebra, we are going to project that equation there on plus z and minus z, and we end up with two equations, and the two equations are written down there. And we see that what we end up with is this kind of new object, which is an operator that is sandwiched between a bra and a ket. And then we have in the blue boxes, we have all those these amplitude, those probability amplitudes that we get. Of course, we know that these are the components of the vectors. So for example, on the right hand side, we see the column vector that represents the ket phi in the plus z minus z basis, while we can build a row vector, actually a column vector as well, for the ket psi on the plus z minus z basis as well. And if we do that, we find that these two equations can be written in a compact form. So these are the two equations I was talking about. Can be written in a compact form like this. So in other words, we find this usual correspondence between these two coupled equations and kind of a matrix vector relationship. But we already know what the two vectors are. These are representation of two kets in the plus z minus z basis. And it turns out that the other term, so the matrix, the 2 by 2 matrix, is a representation of the operator A in the plus z minus z basis. So this is what we find. And again, we use that notation showing that this particular representation is not the operator itself, it is a representation of the operator in a given basis. Okay, so now let's try to see an example of this. We are going to use a fairly simple example, which is the projection operator. So actually, projection operators, we're going to look at both of them. For P plus, the general formula we use is right there. So we just sandwich the operator from a bra and a ket on the left and the right hand side. And of course, what we find very quickly is that we get a 1, 0, 0, 0 matrix. I'm going to let you figure it out. That's pretty simple, that if one of the ket or bras is a minus z, the projection P plus will automatically involve a plus z minus z, where minus z plus z amplitude, which is 0. So that's the reason why all the terms are 0, but the first term. Similarly, we can calculate P minus, and we obtain 0, 0, 0, 1. Of course, just so you know, if we add those two P plus and P minus, we get the identity matrix, just like the fact that if we add the P plus and P minus operators, we get the identity operator. So of course, very often we forget to say that one is an operator, the other one is it's merely its representation in the basis, but it's actually a good idea to try to keep that in mind, the difference between representation and the abstract object itself. Okay, now another operator we've seen is JZ, and JZ we know that it should be pretty easy to calculate in the z plus z minus z basis, because we know that JZ operating on plus z is h bar over 2 JZ, and JZ operating on minus z is minus h bar over 2 minus z. And of course, we get something like this. In other words, we find that JZ in the basis SZ is diagonal, which is not very surprising. You've seen probably before in linear algebra that when you have an operator, if you represent that operator in the basis of these eigenvectors, you obtain a diagonal matrix. In fact, we often say the operation of finding the eigenvectors is called a diagonalization of the operator. This is pretty straightforward, and of course, the value of the diagonal elements are the eigenvalues that are written there, h bar over 2 and minus h bar over 2. So nothing really surprising, but this little framework we're using for the representation of the matrix seems to work pretty well, and it's going to come in handy for many calculations and operations that we will perform in this quantum mechanical introduction to quantum mechanics. Okay. Of course, we can calculate the eigenvalues again, and then we end up with the right value. This is exactly what I told you with respect to the previous slide. Okay, now let's try to think a little bit about the adjoint operator. So far, the adjoint operator, I didn't tell you really what it was, other than it's the equivalent operator to obtain the bra version of a ket version over which the operator operates. That's all we have said so far. We found that it's Hermitian if J is equal to J dagger. In other words, if it's a self-adjoint. So far, so good. We find also that it was unitary if the A dagger was equal to A minus 1. But we still didn't really say anything about the general operation between A and A dagger. Well, we'll be able to do it right now. Okay, by definition, the adjoint operator is obtained by the formula. If A allows you to go from psi to phi, then A dagger will allow you to go to phi to psi, but in the bra version. Okay, that's the definition of an adjoint operator. So we can take the inner product on the left, of course, with the arbitrary ket psi, for instance, and we end up for both cases. So the ket psi for the right for one equation, and the bra chi for the other case, and we obtain those two equations again. And of course, we know that the probability amplitude chi phi is actually equal to the complex conjugate of phi chi. Okay, so that's something we know. We have already established this in probably lecture number 1. And then when we do that, we find that the only way for this to be true is that the matrix element phi A dagger chi is equal to the complex conjugate of chi of the matrix element chi psi of A. So just to make sure that things are clear, let's use, for example, I and j, and suppose the I and j are particular basis set. We find that the matrix element of A dagger is the complex, A dagger represented in a matrix form is nothing but the complex conjugate of A, right? Because we have changed A and I and j, which corresponds to the transpose, and conjugate because of the star. So far we had not yet proven that, actually. We probably all thought about it, but we had not proven so far that the representation of the adjoint operator is actually the transpose conjugate of the representation of the operator that we start with. So we just done. This is done now. So we can use that property of the representation. Okay, so this is what's happening about this case, and of course, in particular, we have. In particular case, we have a Hermitian operator. It's obtained when the Aij is equal to Aji star, of course. Okay. Now let's try to think about the matrix representation of a product of an operator. Well, which all we have to do now is to insert the identity operator that we have seen so many times for a complete basis, and we just insert that in between the operators. That allows us to express the elements there as a sum over the product of matrix elements. And of course, we find the usual property of that the matrix element of a multiplication of two operators are obtained by the formula on the right-hand side, where we circulate the inner index the fastest. Okay. Same thing for the adjoint of a product. What are the matrix elements of an adjoint of a product? Well, we know that we can certainly write it this way. We just put in the parentheses the right place. We know that the adjoint is going to be obtained by that formula. But at the same time, we know that, so just by applying what we need to apply, so that means that the AB dagger, it will be equal to B dagger, A dagger, right? Because if I wanted to go directly to the ket, to the bra phi from the beginning relationship, I would have an AB dagger that should operate on the bra psi. Phi. So we obtain this formula. Again, nothing really surprising, but do not forget it. The adjoint of AB is equal to the product of the adjoint, but with a permutation. All right. So now we have made quite a lot of progress in representing projectors. We've shown how to represent JZ. We've shown how to represent the projectors. And we've also seen that by looking at the representation, they have very specific properties. For example, the adjoint is just the transpose conjugate. That's one thing. And we've also seen about the matrix element of a product. Okay, so now let's suppose that we are working in a given representation, but we wish to change representation. This is what we are going to do in this section. So let's look at rotations. So we can certainly use a rotation to rotate a ket into a new ket. And here it's not a typo. We are using the dagger. You know, if R is unitary, R dagger obviously is unitary. So I could use R dagger to operate on a ket. Okay? Of course, another way to look at it, we know that the dagger is the rotation of the opposite angle. So it's like rotating in an opposite angle. So this is R dagger that can be applied to a ket. So this is one of those operators that can operate either on the right-hand side on a ket or on the left-hand side on a bra. Okay. So as I said, rotation is just, the inverse rotation is just the adjoint. Okay. And we can represent the state psi prime that we obtained from rotation. Again, we can represent it as a column vector on the plus z minus z basis, and we can simply substitute the psi prime by r dagger psi from the definition, actually from what we are looking for. So far so good. We have two vectors. Okay. So let's keep going. We can now that we've written this, we do no longer have the memory of representing R dagger operating on the right-hand side. We could certainly have R dagger operating on the left-hand side. we don't know. When we write it the way we've written there on the third line, it could be either way. We just know that when we started to write those equations, we operated our dagger on the right hand side, but it could certainly apply on the left hand side. So for example, let's see a little bit what's going on. Let's suppose that we can get the plus x by the rotation around the y-axis of plus z. If we do that, and we've done that earlier in this screencast series, we obtain the ket vector plus x on the basis plus z minus z. We use here real numbers because, well, this is the reference we used. Okay, we could use an overall phase, as we know, but it doesn't really matter in this case. So similarly, we can calculate minus x as a rotation around the y-axis of pi over 2 for minus z. And we obtain minus x. Okay, you can check that minus x and plus x are perpendicular, and we can obtain plus minus x rotating from plus or minus z around the x-axis. Of course, we can also write the bra version of this using our dagger. Okay, nothing really new here. This is just a summing up from what we've done before. So this is what we have. Okay, this is a reminder of what I had on the previous slide. Okay, now let's try to think about how we move from the SZ basis into the XX basis. So we can actually think about going back into my problem of psi prime obtained by rotating psi counterclockwise, I mean actually clockwise in this case, since it's our dagger, around the y-axis, and we obtain psi prime from psi. So we get this, okay? So let's try to think a little bit. This is the most important thing. So the first three parts, we've already discussed them a few slides ago. But the last equality, so the right-hand side of the last equality, we find that instead of thinking about our dagger applying on psi, we get our dagger applying to the left on the bra plus z. And we know that our dagger applied to the left on the bra plus z, we obtain plus x, I mean the bra version, plus x, and same thing for minus x. So in other words, what we've been doing there is to say, and this is very important, that the z representation, the representation in the SZ basis of psi prime is exactly the same numerically as the SX representation of psi. That's what, in plain English, what these equations there mean. So what's very interesting here is that if we had simply rotated the basis, or if we had simply rotated the vector, this something is equivalent there. Okay? In one case, we rotate in one direction with our dagger on the ket, and the other case, we rotate in the other direction our dagger on the bra, because we know that our dagger on the bra is actually going clockwise or counterclockwise, while our dagger on the ket is going clockwise. Yes. Okay. All right. Very good. So in other words, we have this, and we see that we have two equivalent pictures. We either rotate the axis or we rotate the basis, and we obtain the same object. Really, the physical reality is that the numbers are the same. Okay. So in other words, we can see that we can write, we can go from the SX basis, or from the SZ basis to the SX basis. And let me remind you that when I say the SX or SZ basis of a ket vector, we are really talking about a column vector. And then we can use a matrix representation to go from one to the next. And here, all I have done really, writing this equation that you have on the screen, is really writing the identity operator. So I invite you to develop these operations, and then that's what you will find. Now we can go one step further and replace the plus x, the ket, the bra plus x, by a rotation r dagger on the bra plus z, and so on and so forth for the other part of the matrix. And when you do that, you find that the change of representation for the ket psi from plus z to minus z is obtained by a matrix. And the matrix representation, so you see, it looks like the matrix is the representation of our dagger. So if we use our dagger, we can actually move from the plus z representation to the plus x representation. Okay. So we can also do exactly the same math for the Sx to the Sz basis, and in that case we find a matrix that says S, which is exactly the same as before, but complex conjugate. Okay, so what we've just done, we just found that we have a new matrix which is the matrix representation of the rotations that is actually such that S dagger S is equal to 1. Of course, we have that since S is the representation of the rotation. Therefore, it obeys the same properties as the properties of the rotation, which itself is unitary. And unitary means that R dagger R is equal to 1. In other words, R dagger is equal to R to the power minus 1, so the inverse. Okay, now let's try to go one step further. And now that we know how to change the representation of the vectors, let's see how we change the representation of the operators. Okay, so in this case we have the Sx representation of the A operator, and we can write it using this expression to connect the X representation and the Z representation. And again, what we've done here, we have essentially simply expressed the identity operator for plus Z minus Z twice, and for plus Z minus Z twice on the second line. And so we have put it back in a matrix representation. I do invite you to calculate explicitly, so to develop explicitly the second line, just to see that it's obviously simply introducing the identity operator. Okay? And when we do this, of course, we do see what's going on. What we've done is to find that the A representation, the X basis, is obtained by S dagger AS, where S, A, and S dagger and S are obtained the same way as we've done before, and A is simply the representation in the SZ basis of the operator A. So I'd like to tell you that really the left and the right hand side, so the S dagger and S, what they really are is the representation of R dagger and the representation of R, which turns out that allow us to write it in a very simplified way. Okay, so we can think about a number of applications, and you know those formula, you can either remember them or you can just know where to find them. But what's important is to know how they work. So for example, S, which is again the SZ representation of the rotation operator, is going to be obtained by this equation. Again, you just remember what the expression of the ket plus x and minus x are in the plus z minus z basis, and you obtain that matrix. And you can, for example, go for the JZ that we know is given by the central matrix there, which is 1, 0, 0, minus 1, so the diagonal element, diagonal matrix 1, minus 1. And then you multiply on the left by S dagger, on the right by S, and you obtain the representation of JZ in the Sx basis. So some of you might actually be recognize that that is one of the Pauli matrix. And we will see, in fact, why it's a Pauli matrix in a future lecture when we work more on operators, and I mean when we work more on the spin moment and so on and so forth. Okay, so the S matrix that allow us to change from one representation or another, we can also use it for an operator. Okay, now this is, so the previous work is is really important is not so much to memorize it, but to understand how we get it. And then once you have that, you can reuse it over and over, and then you will understand what's going on. Now, before we conclude this chapter, I'd like to talk to you about expectation values, which is important. We've seen before what it was, and I'm just going to spend a couple of slides to introduce you what the expectation values are. So remember, an expectation value, for example, for SZ for a state, for the ket psi, is obtained by this, okay? Which is the realization of the measurement times the probability that we have that measurement. That's exactly what this equation is. Now, we could also write the same value just in a matrix form. So we have a column vector, so it's a bra, it's a representation of the bra psi. A matrix representation is the representation of JZ, and then the column representation, which is the column representation of the ket psi. In fact, it's exactly what we need. If we do that, we find that the expectation value of SZ is simply the matrix element, one way to do it, the psi-psi matrix element of the operator JZ. This is an extremely important formulation, which we have actually proven in the general case for using the identity operator. We've done that during the recitation. But this is a very important notation relation that we will use over and over again. For example, if we think about the expectation value of SZ for the state plus X, we know from a Stern-Gerlach experiment, one of the Stern-Gerlach experiments, that if we have a plus X state and as an input for an SGZ, so Stern-Gerlach Z experiment, there is a 50% chance to go a plus h bar over 2 and 50% minus h bar over 2. Therefore, we know the expectation value should be 0, so we can be equally minus, equally plus. And indeed, if you use the formula we just looked at, that's what you have. So you find exactly the same, the right answer here. And of course, if you use a different basis, you should get the same answer. Clearly, you should always find the same answer, which would be equal to 0. So this is something that's quite interesting to do, and it's going to come in very handy. Now, so far we have spent quite a bit of time talking about Stern-Gerlach experiment and building a space, the quantum space of Ketz and the dual space of Bras and computing amplitudes and computing adjoint, computing rotations operators. But frankly, everything is pretty abstract so far, right? We can say the connection to physics is a little bit blurry. It is not really blurry. It is just that we have to establish a formalism to be able to move forward with our understanding of quantum mechanics. So we have very strong footing now to start to do to look at quantum mechanical behavior. What we are very happy about, though, is that everything we have built so far can completely account for every observation made in the Stern-Gerlach experiment, including the counterintuitive one. Now, many of you who are taking this course have taken quantum physics before. And the first thing that you've been told as quantum physics is that the reason why electrons are so weird in the quantum mechanical world is because they behave like waves. And then you may wonder, well, what does any of what we've done so far, what does it have to do with waves? Well, the reality, it's very little so far. So what I'm going to do to conclude this chapter is review a connection on how we can use the formalism of Bra and Ketz that we just established to show that indeed that description naturally applies to waves, okay? And we are going to end this chapter with kind of a very, very striking result that we have. Because we are going now to analyze light as particles using photons. And this is what's going to help us understand a very, very, very strong properties of this formalism of quantum mechanics. Before we start, I'd like to remind you a little bit what a linearly polarized and a circularly polarized wave are. Well, you know the wave, it's going to propagate along the t-axis there. And it has a z component, and it has a y component. And those two components, of course, form a vector. And this is what we are going to look at. So it's a plane wave. I got this animation from YouTube there, and with the license, a Creative Commons attribute license, and this video is actually very, very good for explaining the linear and circular polarization. So basically, we start here. We're going to look at the wave going into along the black curve, and we have two orthogonal waves, and they will be in phase. That means that they get the minimum and the maxima at the same time, right? That's what it means to be in phase. And of course, the sum of the two is the resultant wave. It's the green arrow. And what you see is that green arrow is actually staying in a line. It's a line. It's linear. It changes its length, of course, but it's a line. So it's a linearly polarized wave. That's what we call a linearly polarized wave. Now, we can see this, and it only works because the two the two components are in phase. Now let's suppose for a second that they are dephasing by a quarter cycle. So a quarter cycle is pi over 2. And that means that when one is maximum, the other one is minimum, and the other way around. So what happened now, if you look at the resultant with a green arrow just now, we see that the effect is to see that the resultant actually move around a circle. So this is what we call a circularly polarized. So the only difference between the linearly polarized and circularly polarized is simply related to the dephasing between the two components. Okay? Of course, in general, the dephasing is not pi over 2. It can be anything. And in that case, we have the general case of an elliptic polarization. Okay? So the general case is an elliptic polarization, and the special case are linear polarization when they're in phase, or circular polarization when the dephasing is pi over 2. So this is going to come very, very handy. We see that the polarization of the wave is directly related to the phase difference between the two components. That's what matters here. Okay, so we are going to suppose we have a photon polarizer, either horizontal polarization or vertical polarizer. So it's going to stop for example, the one that I have on the slide here is a vertical polarizer. It's going to stop every light that has a linear polarization horizontal, and it's going to let all the light that has a linear polarization vertical through. In other words, we can write this as one case we have when we have an horizontal polarization that the output state is an X state, and when we have vertical polarization, we have a Y state. And we are going to use our notation of kets, X and Y. I do that because I can suppose that those two states, X and Y, form a complete basis. Indeed, no matter what I enters, what kind of linearly polarized wave comes in this one of those apparatus, there will be a superposition of an X state and a Y state. That's what it means. And on top of that, if I enter with an X polarization with a filter that has a linear polarization in the X direction, the probability of finding it outside is 1, and same for Y. On the other hand, they are orthogonal, because if I try, for example, to have a linearly polarized horizontally wave going into a filter that has a vertical grading, then the probability of going through will be 0. So that's very nice, because that means that any photon state can be written that way, where I have simply applied the identity operator. And I obtain, of course, some coefficients that will tell me how much of the wave is in the X direction and how much of the wave is in the Y direction. Okay, so far we've not done anything else than using the notation and the framework that we've developed for the Bras and the Kets. Now suppose we rotate the polarizer. Okay, we're going to rotate the polarizer by an angle phi, and of course the new state X and X prime, which will be the state that come out of those polarization of the grid that I use, the filter that I use, will be obtained simply again by those expressions, which you should be familiar with by now. This is exactly applying the identity operator in the X-Y basis, and we do that for both X prime and Y prime, which will be the two principal directions for the rotated filter. Okay, so far so good, nothing really crazy. The coefficients are going to be obtained by making sure that this result comply with our classical interpretation, which is that when we rotate a wave like this, the X component will be obtained from the EX prime component times an angle cos phi, and the Y component will be obtained by the EX prime component times sine phi. Okay, this is the usual rotation, nothing really new here. We can actually go further than this, because we know that the intensity of the light will be proportional to cos square phi and sine square phi, which seem to mean to us that the coefficients of the amplitude probability should be cos phi and sine phi, since what we measure is the square of it, which is cos square and sine square. Okay? On top of that, we know that cos square and sine square add to 1, so we have a normalized state, which is not, again, very surprising. This is a good property. So we could look as well for the light that goes along y prime, and we do the same exercise, and we obtain, again, we have minus sine phi and cos phi. This is simple geometry. At the end of the day, what we get is that the x prime and the y prime state, which I obtained from rotating the filter by phi, by an angle phi, can be expressed from the basis xy of the filter that has not been rotated. Okay. Of course, we can argue that here maybe there is a phase factor on one of those. We are going to ignore it for now because we can show that we do not need it to explain the physics, even though I cannot provide you a full proof why we don't need a phase factor. At least I cannot prove it here in this context here. But what matters is that we are really working and describing the wave as a particle, since everything is written as for a photon. Okay. Now here is where the strength of all this is coming into play. Of course, yes. Before I go there, this would be the rotation matrix that we've seen before as dagger and S to go from one basis to the other, and same for the. If you go to the other side. Now here is when things become very interesting, and it's the reason why I showed you this little YouTube video to start with. We can think about a right circular polarized wave and a left circular polarized wave. And these are obtained from the wave along the x direction plus the wave along the y direction, which has been shifted by pi over 2. As you remember, pi over 2 is nothing else than, in complex plane, corresponds, if you use the complex exponential, correspond to the number I. And if you have a left polarization, it corresponds to minus I. So you're rotating one direction or the other. That's how we explain the presence of those complex numbers. It's really related to the circular polarization. Classically, this is the answer I showed you there, where we add the x direction and the y direction. Same thing as you've done in electromagnetic theory that we can use here in the quantum mechanical phase. Okay, now, what do we do with this? Well, let's suppose now that I am interested in a circularly polarized state in the prime basis. So in the basis where I rotated the apparatus by an angle phi. I can just simply substitute the x prime by its expression in the xy basis and the y prime in the xy basis. You can look at 2 slides above. And when I do that, I end up, when I put everything together, I find that r prime will be related to r with that term in the front. And that term, of course, is just the complex exponential of minus I phi times the rotated angle. So this is quite surprising. Actually, it's not surprising in that sense, in the following sense. If you have a circularly polarized state R, and you rotate your apparatus, you expect that what you get from that is still a R prime, is still a right circulatory state, but you do not change really anything about the physics other than a phase factor, which is exactly what you have here. So we are simply rotating the state, okay? But this is really the most important thing here in the box with the blue arrow. We find that it's the same as applying a rotation operator, just like we've done before, around the z-axis with a phase factor that's obtained by some operator jz, some generator rotation, that we have times phi over h bar. The reason why this is really surprising here is that we don't have a factor of 2, a factor of 1/2, really, that we had for the spins. So what it means really is this. It means that if I write the equation the same as the previous slide, it means that this seems to indicate that the state R, so the right circulatory wave, is an eigenstate of Jz for eigenvalue h bar. In other words, the particles of light, which we know to be photons, correspond to a spin of 1. Remember, when I was applying Jz to plus or minus z for the Stern-Gerlach experiment, I find the eigenvalues to be h bar over 2. That was related to the magnetic moment of the system, that was h bar over 2. So this was for spin 1/2 for electrons, and here for photons we see that we have a spin 1. So just this is coming all directly from this formalism that we have used so far. So this is the strength of the formalism that we have been developing. Of course, we can do the same for the left circular polarized wave and get like this. So we can conclude the photons have an intrinsic spin of +1. So this is, of course, a completely description of wave-like development of electrons. And we see that everything seemed to work together very nicely. And this is the reason why we have such a strong framework to understand quantum mechanics. And this is what we are going to do in the chapters to come. Thank you very much.